So in the previous video, we took a look at and basically an introduction to Kafka, what makes it unique. So let's dive a little deeper into the Kafka design itself. So Kafka is actually a circular buffer. Now, what circular means is the fact that okay, firstly, what does a buffer mean? A buffer is just a data storage area which allows you to keep adding new things to it at the end, and it keeps it in it basically keeps the data available temporarily. So the temporary nature of a buffer refers to the fact that you don't use this for permanent storage of data, because at some point the data ages. So Kafka's design was such that it was catering to message exchange between different microservices or between softwares, between systems. But usually there's going to be some kind of a time value attached to that data. And so what it made a conscious design choice was every data will have a time to live, and that time to live will basically expire the data once that time to live is complete. And that time to live is a concept that applied at the level of the entire Kafka cluster. Optionally, you could actually change the time to live for a specific topic as well, but you couldn't change it for every message within a topic, right? It applied at the topic level, and that's about it, right? So for a topic, if the time to live is, let's say, set to 7 days, which is I think the default still, then every message that comes in would get expired once 7 days are done from that message, right? And this is it's actually a pretty simplistic design from a point of view of implementing it within Kafka, but it has a profound implication on the rest of the architecture around streaming, right? That depends on Kafka. So what this means is, you know for a fact that the data aren't going to be long-lived. So it is temporary logically. Obviously, it's persistent in the sense that the data is actually stored in disk, and you don't have to worry about the data being temporary and data being lost if you don't consume. But there is a time to live. So even if the consumers go away and come back at a later point in time, it cannot be more than the TTL, the time to live of that particular topic, if it has to be able to consume all the data without losing it, right? So why was it done this way? It's because of the sequentially increasing nature of the offset, right? Obviously, the offset number will keep increasing, but at some point, for the purposes of practicalities, it's going to hit the maximum number that can be coded up in a big int, right? Or in a big integer, 16 bytes. So therefore, 8 bytes, right? 8 bytes. Yeah. So therefore, at some point, you're going to run into more than that much amount of that many number of messages, right? Like 2 to the 64, right? Yeah. So that's like billions of messages, but even that's a limit, right? It's not unlimited, it's not unbounded. So at that point in time, what needs to happen is, obviously the number cannot be incremented any further, so it starts all the way from 0 again. So if the messages were long lived, then you couldn't reasonably index or create an offset for messages that were much older, which could potentially take it beyond the offset data size, the data type size, right? So therefore, time to live was like a very, very innate concept of how Kafka was designed. That's what makes this a buffer, right? It's circular in the sense of this offset going all the way to max begin rather, and then coming back to 0, right? So think of it as a gigantic queue that's actually circular, right? Going from 0 to all the way to max begin, and then starts from 0 again. So that's the kind of architecture we're talking about for every topic. So yeah, the data is split into topic and partition. We spoke about that. In practice, on the broker itself, right? We said that every partition is uniquely mapped to a broker, right? So which means that broker potentially has multiple partitions. There's a many-to-one relationship there, but the broker which is in charge of a specific partition, is going to be responsible for making sure that the data of that of the partition is persisted, so that there is no loss. So when the producer produces the data, it's the broker which is responsible for the partition to which that message, that data belongs to. That broker is responsible for acknowledging that, look, I've received your data that's intended for this partition, I've persisted, so you can be rest assured, right? Behind the scenes, because it's just a continuously increasing offset, it's a monotonically increasing sequence of numbers, and you just keep adding to it. It's actually a log file. A log file meaning a file which is actually just having data registered as log events and sequentially getting appended. Right? How long does this append go for? It goes up till a particular size, and that size is configurable. Typically, it's about 1 gigabyte per size. Obviously, for large scale implementations, you might want to tweak that. So, which means that the log file, let's say, which starts at the head of the queue, which is like 0, goes all the way till the file reaches 1 gigabyte in size, right? And then once it reaches that point, then a new file is created, and this file is closed, which means this file was open for appends until the point that it reaches that size, and then after that, new file is created, and the new file obviously is going to pick up from the last of the offsets of the first file. So this way, for a partition which is like for a topic which is storing massive data, you'll have multiple such 1 gigabyte files, and you could easily index into that file simply by looking at the file name naming convention. So the broker will look at the file naming convention and know what offset is starting for that particular file. And so if as a consumer you come and say, give me data for a particular offset, the broker would know in that partition, this is the file that particular offset corresponds. It's there in the name. It doesn't have to go look through the data, right? So that's again a very nice design, but it makes it easy for it to look at a particular data set. What's even more interesting is that the data that's being written to in the current file, which is still not closed because it's still not reached the threshold, that data is actually firstly in the file system cache, which is actually part of the operating system cache, and the file system is responsible for writing to disk, right? So the cache to disk sync is something that any operating system guarantees, especially Linux, and Kafka is Linux based, right? So this makes it conducive for it to acknowledge the data the moment the producer acknowledge the data to the producer that it's written the data the moment it's actually writing it to the file system cache. And when it writes to the file system cache, it's actually writing in memory. So the read that comes in at that particular point in time is actually directly going to read from memory. It doesn't have to go to that file on the disk. So that's what makes it very good at serving the data set in real-time latencies. So the circular buffer obviously means that the oldest messages are deleted, and therefore there is a certain like I said, time to live and such. But apart from this, the file construct, meaning data is only appended to, right? There is no data, I should say, deletion or updation that happens in between, because the data is actually continuously, monotonically increasing in terms of offsets. So that makes it again a very powerful paradigm, because you could always go back in time and play back exactly the same data that was there, right? Deterministically, you'll get the same data. You won't have to worry about the data having been changed, right? That doesn't happen. Okay, so like we spoke about, it's the consumer or the client that's responsible for tracking what is the offset, not the Kafka server, right? So which means the consumer is responsible for taking delivery of data. It's not Kafka that's responsible for it. Kafka is only responsible to acknowledge to the producer that, look, I've got the data, so you can move on, and that's about it, right? The consumer has to do their work with respect to consuming data and tracking offsets. Okay, let's take a look deeper into what the partitioning scheme looks like. We didn't speak about, we spoke about partitioning as a mechanism for parallelization to get more throughput. In fact, what also happens and rides on top of the partitioning concept is the notion of replicas. So replicas are basically are created by copying a partition live, right, as it gets created, and the copy is guaranteed to reside in a different broker if, of course, more brokers are available. So, for instance, my primary topic, right, rather my topic is comprised of 3 primary partitions: partition 0, 1, and 2. Like we spoke about earlier, the partitions are spread across the brokers that are available. So in this case, it's a 3 broker cluster. So 0, 1, and 2 are spread across the 3 brokers compulsorily. Now, when and those are indicated in red, right? So those are the primary partitions. Now, when the read or write, etc., all of that happens, all of it happens on the primary partition, right? And then the primary partition acknowledges and responds back with data, or acknowledges the write of the data, etc. At the same time, when the writing of the data is happening to a particular partition, Kafka will take the replication factor that's configured. By default, it's 3, including the primary. It takes the that data, which is actually sent to that partition, and also sends the same data to the 2 other places where the replicas of that partition exist. Like in this case, broker 2 and broker 3. So, and that happens through a peer-to-peer data exchange, right? From partition 0 of broker 1 to partition 0 of broker 2, partition 0 of broker 3. So that in-sync replication is something that you can configure, right? You can say, I want to wait for all the replicas to acknowledge that they've written, and only after that, the primary will acknowledge back to the to the producer. Or you could say, I'm okay to have these partitions be eventually replicated. So that could take a bit of time, but I'll immediately acknowledge. So that comes down to what kind of availability semantics that you want from your Kafka implementation. But by default, partition 0 partitions, replicas of partition 0 are also expected to acknowledge, required to acknowledge to the primary, and then the primary declares that, okay, I'm done acknowledging your write, so you can move on. That's what it tells the producer. The advantage of that is, in case broker 1 fails for some reason, because of commodity hardware, like I said, because of memory failures, compute failures, whatever, there is the replica that's available in at least these 2 brokers. And by having 2 replicas here, at any point in time, the cluster will actually withstand the failure of 2 machines, right? So you can scale it up to like even 100 clusters, rather 100 machine clusters, and where you have 100 brokers. Even at that scale, if your replication factor is 3, rather there are 3 replicas in total, replication factor is 2. With the primary and the 2 replicas spread across the 3 brokers that in which they are present, the cluster can withstand 2 machine failures, like 2 broker failures at the same time, and still not lose data. So that's actually a pretty powerful guarantee. Okay, like I said, the partition 0 and its replicas are kept in sync. Likewise, partition 1 as well. Likewise, partition 2 as well. One thing I want to point out here is that the replicas are not used for reads. And the reason for that again is the broker is anyway going to spend resources reading from the primary. So we might as well just make the primary take up all the resources available in the broker that's available. So let's not actually burden it with more replicas also trying to read data from there, right? So the replicas are meant for availability purposes, and they come into action only when the write happens to the primary, and then they are kept in sync, not for reads. Okay, so we just spoke about this producer. How does it happen? So the producer writes to a particular partition, and that is determined using hash partitioning or round robin, like we spoke about. And then from there, that partition is responsible for writing to the replicas, and then the replicas acknowledge, and then they respond back to the client once all the acknowledgements are in. Okay, so what about consumers? Unlike PubSub, here there is no notion of a subscription which is maintained by Kafka. Instead, there is a notion of a consumer group. A consumer group is basically a grouping of consumers which together are supposed to consume basically from a topic. right? So let's take an example of a Kafka cluster which has two brokers. I'm, also referring to the broker as server here. So server 1, server 2, meaning basically broker 1, broker 2. And within the two brokers, there are two partitions. So in total, there are 4 partitions for that particular topic. By the way, in all discussions that happen, the partitions which are shown for illustration purposes are only the primaries. So you can assume that the replicas are also there behind the scenes, but those are not getting discussed explicitly. So these are primary partitions. So typical consumer obviously needs all 4 partitions for it to get a complete data. But the consumers themselves can be organized as groups, and those groups are effectively parallelizing the consumption behavior. So let's take, for instance, I'm creating 2 consumer groups, Group A and Group B. Group A has 2 consumers, which are 2 different server processes which are consuming, and Group B has 4 consumers, right? Now, because there are 4 partitions, Kafka actually allows the Kafka consumption interface, consumption SDK, whatever you want to call it, that protocol allows the setup of that particular consumer group to map the partitions to the consumer within the consumer group, such that there is an equal distribution of the load, right? So remember that each of these different partitions is responsible for a subset of data. So by grouping, like let's say in the consumer group A's case, by grouping 2 of the partitions to belong to or to be consumed by one consumer, I'm getting that subset of the data being consumed by that consumer C1, and the remaining will come from remaining partitions, and the remaining data set is getting consumed by consumer C2. So in totality, consumer group A sees 100% of the data. Now, in the case of consumer group B, where there are 4 consumers, the mapping of the partition to the consumer is such that all the consumers get used. So in this case, 1:1, right? 1 partition to 1 consumer. So this mapping, this parallel consumption, all of that is handled by the consumer protocol. So you could actually have consumer groups dynamically defined, like I said, because each consumer group maintains its own offset, and consumer group B's offset is independent of consumer group A's offset, etc. So all of those different consumer groups can coexist. Okay, so what happens when there is actually a failure? So the primary, which is the replica, or the primary primary replica, the primary partition, that let's say is in a broker, that broker fails. Then when that happens, it's no longer the primary, obviously, because it's not accessible. And behind the scenes, the brokers are the state of the brokers, like availability of the broker, etc. That's kept in sync using a Zookeeper implementation. We actually saw Zookeeper as part of the discussion on Hadoop, one of the earlier week's lectures. So that maintains state of the cluster, right? Maintenance of the state of the cluster allows Kafka to reason about the fact that the primaries, the broker has failed, and therefore all partitions which are whose primary copies are at that broker, they get marked as failed. When they get marked as failed, their appropriate replicas, one of them is promoted as the new primary, right? And those replicas could be anywhere in the cluster. So one of them is actually promoted as the new primary, and then life goes on, right? Now, let's say this particular leader comes back up at a later point in time. By that time, the new primary that's actually been nominated or being promoted rather will get additional data, obviously, right? Because it's the new primary, so it's going to be recipient of newer data sets that get written by the producer. So when this original primary comes back up after, let's say, a day or 3 days or whatever, then the replication, firstly, Kafka's state management recognizes that actually this is a replica that is valid. It used to be primary, it's no longer the primary, and at that point it actually automatically catches up with the new primary that was promoted a few days ago, and it continues to be a replica, right? The primary that comes back up, the whole primary that comes back up continues to be a replica until and unless you make a change, right? And you can trigger a rebalancing such that the partitions again are uniformly distributed across the brokers. The primaries are uniformly distributed, but that doesn't happen automatically because the rebalancing act is typically an expensive proposition. But nevertheless, right, availability by default is designed in the code design of Kafka. Okay, so before we go further, I'll just take a pause here and we'll continue with the topic of consistency, what happens with right semantics and such in the next video.